Okay, so we are looking for rules, both explicit and recursive, for geometric sequences. So in this first one, we have gn is equal to 192, 144, 108, etc. So the first thing we need to do is find out the common ratio. So in other words, what value would give us 144 when multiplied by 192? So that would give us that r is equal to 144 over 192, which is equal to 0.75. We can confirm that 108 over 144 is also 0.75, so it is geometric and it is our common ratio. So the first thing we want to do is the recursive rule. And basically what the recursive rule does is it says, what are the two elements that specify this particular sequence? Well, it is that the first term is 192 and that the rule for going to the next term is that term times 0.75. So the recursive rule says that g of 1 is equal to 192 and g of n plus 1 is equal to g of n times 0.75. We also say that n is going to be greater than or equal to 1 because it would make sense to have, let's say, n is equal to 0, because that would give us g of 1 is equal to g of 0 is times 0.75, etc. So all this does is it says take a first term of 192, multiply it by 0.75 to get the second term, multiply the second term by 0.75 to get the third term, etc. And that gives us our recursive rule. Our explicit rule, on the other hand, says we really want to find an equation for this so that we can find the value of the nth term without having to know the value of the term before that. So our explicit rule is one where we can say that g of n is equal to, and what we want is an expression where it includes the value of n, and so if we want to know the 100th term, we just plug 100 into our expression and we get the value. Well, we know to get, for example, our 10th term, we would have to take 192, we would have to multiply by 0.75, and to get to the 10th term, we would have to multiply by 0.75 one time, two times, three times, etc. And so the number of times that we would have to do that multiplication is equal to n minus 1. Because by the time we get to the second term, we've only multiplied by 0.75 one time. So this gives us our explicit rule, and again, n is greater than or equal to 1. Okay, and again, this should be more or less a review. All right, now we have that we were told that this is geometric. We have missing terms. And so we say, all right, let's say that this term is 4r. This term would be 4r squared. This term would be 4r cubed. And now we have an equation because now we have that 8 is equal to 4r cubed, which gives us that 2 is equal to r cubed, which gives us that r is equal to the cube root of 2. So we have a number of ways we can write this. We could say 4, we could say 4 times the cube root of 2, 4 times the cube root of 2 squared, and then we'd have 8, and then we could say either 8 times the cube root of 2, and then 8 times the cube root of 2 squared. Or we could say that our common ratio r is equal to 2 to the 1/3. So we would get 4 times 2 to the 1/3, 4 times 2 to the 2/3, 4 times 2 to the 3/3, and that's just 2, so that would give us 8. Now we'd have 4 times 2 to the 4/3, and then 4 times 2 to the 5/3. Or we could have found the decimal approximation and just had the numbers 4, and then it's about 1.2599, so we'd have 4 times that, and then we just keep multiplying by that, 1.2599. Okay, let's take a look at our next one here. Okay, so we're first we're not sure what kind of sequence this is, so we're going to see, is it a arithmetic? Well, let's see, we added 9, then we added 11, so no, it's not arithmetic. If we calculate 37 over 26, we will find that that's not equal to 26 over 17. Therefore, it's not geometric. Okay, so the other thing we've looked at are quadratic. And we can see here that we have a difference of 9, we have a difference of 11, and so we see possibly, if it's quadratic, then our difference of differences will be common, which would mean that the next term we would add 13 to give us 50, and that also means that we would add 15, and that gives us 65, so that works. So that means that going backwards, we added 7 to our previous term to get 17, so that meant that it had to have been 10. We added 5 to our term before that to get 10, so that would have had to have been 5. So now we have common differences of 3, 5, 7, 9, 11, so that gives us a quadratic. We're not actually asking you at this point to find the equation of that quadratic sequence, but just to recognize that it is a quadratic sequence and find the missing terms. Okay, so now we're at our basic skill for finding the equation of an exponential curve that passes through a given pair of points. Okay, so the first thing we'll do is we're going to set up our basic equation, which is y equals ab to the x, and that is the equation we use for all our exponential equations. Okay, so now we can substitute in. We have values for x and we have value for y. So we first substitute in, we get 4 is equal to a times b to the 0, and we get 6 is equal to a times b squared. Now when we get b to the 0, that's a special case because b to the 0 always evaluates to 1, which means that would give us that 4 is equal to a. And we can then substitute in and say 6 is equal to 4 times b squared, which means that 1.5 is equal to b, which means that we're going to get that b is equal to the square root of 1.5. And that in turn is equal to about 1.225. So our equation then is y is equal to a, or 4, times 1.225 to the x. Now, I like to use at least 3 decimal places here because when we are raising these numbers to exponents, especially as the exponents get larger, the more imprecision we have in the base that we're raising to a power, the bigger consequences it'll have as x gets large. All right, now let's do this for a second time. So again, we're going to go back to our basic equation, y equals ab to the x, and we're going to set up the 2 equations. 6104 is equal to ab to the 7th, and 7310 is equal to ab to the 4th. So this is a situation of exponential decay because as x grows larger from 4 to 7, our y value is going down, so this might be population declining or something else like that. All right, so now we're going to divide the 2 equations. We're going to divide the top equation by the bottom, although I could do it in the reverse order and I would get the same values for a and for b. So I'm going to get that 6104 over 7310 is equal to ab to the 7th over ab to the 4th. All right, first thing, these a's cancel out, which is nice, giving us b to the 7th over b to the 4th, which, as we know from our exponent rules, is just b to the 7 minus 4, or b to the 3rd. So what we get when we work this all the way through is that we get 6104 divided by 7310 is equal to 0.835. So we get 0.835 is equal to b to the 7 minus 4, or b to the 3rd. So 0.835 to the 1/3 is equal to b to the 3rd to the 1/3, which is equal to b to the 1st equal to b. So what we did was, because we had b to the 3rd and we're trying to get back to b, we're undoing what's been done to b, which is that it was raised to the third, so we raise both sides to the 1/3 power. And when we do that, we get that on the left side, we will have a value of 0.9417. So we have 0.9417 is equal to b. Now we'll substitute that back in, and we'll say that 6104 is equal to a times 0.9417 to the 7th. Or, in other words, a is equal to 6104 over 9417 to the 7th. Okay, so when we do that, we raise that to the 7th, and when we work it all through, we get an a value of 9,296.5. So a is equal to 9,296.5. That makes sense that a would be larger than 7310 because we are, as we said, we had exponential decay, so when x is 4, we have a larger y value than when x is 7, which means that since it's decay, when x is 0, we would have an even larger value for our y value, and that's what we get because a is the value of y when x is equal to 0. So our final equation then is y is equal to a 9296.5 times 0.9417 to the power of x. So what this is saying is that given a starting value of 9296.5 at, let's say, time x is equal to 0, each year we would have a population, if this were a model for population change, each year we would have a population equal to 94.17% of what we had the previous year. What that means is that each year we are losing 100 minus 94.17%, or 5.83%. So that means that we would be having an annual population loss on average of 5.83%. Okay, we don't know that this was about population, but we're just using that as an example. Okay, so now we're going to look at a half-life problem. And we've talked about, we have a couple ways of dealing with these. So let's look at the first one. Okay, so what we know is that the half-life of Tylenol, according to this, is 2.5 hours. So that means that every 2.5 hours, we're going to go from what we have in our blood to half of that. So if we took 500 at time equals 0, then at time equals 2.5, we would have 250. At time equals 5, we would be down to half of that, or 125, we'd be down to 62.5. After 3 half-lives, or 7.5 hours, we'd be down to 0.25. After 4 half-lives, or 10 hours, etc. Okay, so what we know is that for each half-life, our quantity can be multiplied by 0.5. We also know that we took 500 milligrams at noon in this case. And then the question is, between noon and 5:30, which represents 5.5 hours, how many half-lives passed? Because we're saying that if each half-life, the change is 0.5, then the next thing we need to figure out is how many half-lives have passed in that 5.5 hours. Well, we can calculate that easily by saying 5.5 divided by the half-life is our exponent. Well, that should be an exponent. It's not clear there. But because what we're saying is that 5.5 divided by 2.5, which would be 2 and a 2.2, tells us how many half-lives have passed between noon and 5:30. So now when we calculate this of 500 times 0.5 to the 5.5 divided by 2.5, we're going to get a value of 108.82. So this gives us that we have 108, so this equals 108.82 milligrams at 5:30. Okay, so does this make basic sense? Well, we knew that at noon we had 500, at 2:30 we had 250, at 5 o'clock we had 125, so having 108.82 at 5:30, yeah, that makes rough sense. Okay, so let's think about this another way. Let's say that we know that we started with 500, and we know that we had 250 2.5 hours later. So we can set up this equation that 250 equals 500 times b to the 2.5. So now what we're saying is that our value in parentheses, rather than representing what happened over a 2.5 hour time period, or the half-life, it represents what happened over a 1 hour period, and we're then going to raise that to the 2.5 power to represent 2.5 hours. So this would give us 0.5 is equal to b to the 2.5. Now if you think about it, our half-life situations will always end up with 0.5 equals b, which would be the amount of change in whatever unit we're considering. So in this case it would be an hour. And our exponent would be the number of hours in the half-life. So if we were saying the half-life was 5,038 years, we would end up with an equation that looked like 0.5 equals b to the 5,038. And in that case, b would represent the amount of change in 1 year. In this case, we're saying b represents the amount of change in 1 hour. Okay, so now we can do our calculating. We can say that 0.5 to the 1 over 2.5 is equal to b. And when we evaluate that, we get 0.5 to the 1 divided by 2.5 gives us 0.7579. So we get equals 0.7579. And now that represents what happens each hour. So now we can say that the amount we have after 5.5 hours, y, would be equal to our starting value, which we said was 500, times our hourly rate of change, raised now to the power of 5.5. And when we raise, and I'll keep the value on my calculator so it's more precise than even just this 4 decimal place approximation, and I'll raise it to the 5.5 power. And then I will multiply that quantity by 500, and I'll get 108.82, which is what we got using the other method. Either method is fine. I feel like the first method is a little easier, but you have to decide for yourself. Okay, so now they're asking us how long will it be for there to be just 50 milligrams left? Well, we already saw that after 1 half-life we had 250, after 2 half-lives, so at 5 o'clock we had 125, at 7:30 we had 62.5, and then at 10 p.m. we had 31.25, so somewhere between 7:30 and 10, closer to 7:30, we'll have 50. And what we're going to do is we're going to set up our equation. 50 is equal to, and we could use either of our 2 equations, but let's use our equation that we created here. So 50 is equal to 500 times 0.7579 to the x. And that's the equivalent of saying if we divide both sides by 500, 0.1 is equal to 0.7579 to the x. And basically what we're saying is how long does it take a quantity, in this case 500 milligrams, to decay to 1/10 of the original quantity, again in this case 50 milligrams. And so we don't yet know how to find the inverse of this exponential equation, which is really what we need to do in order to be able to solve for x. So we're going to graph it. We're basically going to say, all right, we know we're going to have a situation. We're going to say y is equal to 0.1, and we're going to have this thing that decays. And we know that when x is 0, we're way up at 500, so this is not drawn to scale. But eventually, our exponential decay equation will cross our line y is equal to 0.1. Or I'm sorry, because we divided by 50, our our equation has a y-intercept of 0.7579. So this would be 0.7579, and eventually it'll cross and intersect our line y is equal to 0.1, and this is something that we will just do on our calculator. Okay, so when I did this, I found that these two intersect when x is equal to 8 let's see this value again, 8.31. So not far off from what we said. It took a little more than 8 hours, so a little less than 8 1/3 hours for there to be just 50 milligrams left. Okay, so now we continue onward to our next problem. Okay, Andre Levesque deposited 5,000 euros in an account at the start of 2006. He forgot about the account until the start of 2016. So when he checked then, the funds in the account had doubled. What was the average annual rate he received over that 10-year period? Okay, so what we're saying is that at the end of, so after 10 years, he had 10,000 euros, and that's equal to 5,000, his original deposit, times some number, b, we don't know what that is, and it's to the 10th power. So that means that when we divide both sides by 5,000, we get 2 is equal to b to the 10th. Basically, we're saying that some number when multiplied by itself 10 times is equal to 2, because that's the factor by which the amount of money increased. So if he had had 20,000 euros, it would have doubled to 40,000, and we'd still end up with the 2 equals b to the 10th equation. So to solve that, we take the 1/10 root, or 2 to the 1/10 is equal to b to the 10th to the 1/10 equals b to the first equals b. And that is going to give us the value, so 2 to the 1/10 gives us 1.0728, we'll say. 1.0728. So what this means is that each year it was multiplied, his money was multiplied by 1.0728, and that's to say that it grew at an interest rate of 7.28% per year. Okay, so now we'll look at a compounding problem where we'll look at the comparison between investing $3,500 at a rate of 3.6% compounded daily, or a rate of 3.65% compounded twice a year. Okay, so compounding daily means that we started with 3,500. We're multiplying by 1 plus our interest rate expressed as a decimal, and we're going to do that raised to the power of the number of interest payments. So the way compounding works when we're compounding daily is, instead of doing one rate payment of 3.6%, we're going to do 365 payments, but each one is going to be at an interest rate of 3.6 divided by 365. So we end up with this, 0.036 over 365 raised to the power of 365. Okay, so these two numbers really have to match, because this represents what we're dividing the interest rate payment by, and this represents how many payments we're going to make. So if we were compounding quarterly or 4 times a year, then this denominator here would be 4, and this exponent would be 4, assuming that we're talking about a period of 1 year. If we're talking about a period of 5 years, we would have to multiply the exponent up here by another 5. But we can compare just by doing 1 year. Okay, so when we do out that calculation, we get 3,500 times 1 plus 0.036, and the 0.036 is divided by 365. We don't divide the 1 by 365 because the 1 represents the original fund, so that we're not dividing that. And all of that is raised to the power of 365, and that gives us a value of 3,000 $628 and 29 cents. So we'll just round to the nearest cent. Okay, we're compounding this to 3,500 at an interest rate of now 0.0365 to represent 3.65%. And now we're told we're compounding twice a year. So we're dividing this by 2, and again, our exponent has to match this, assuming we're talking about 1 year only. And when we do this calculation, we are going to end up with, let's see, 3,500 times 500 times 1. Sorry about the delay. And raised to the power of 2. And now we get 3628.92. Okay, not a big difference. This one has a higher underlying interest rate here at 3.65%, but because we're compounding the other one daily, it almost catches up, but even at compounded daily, it still doesn't quite catch up. Okay, next problem. So these are just basic solving problems. So we're going to get 20 is equal to 4 times b to the 5th, which means when we divide both sides by 4, we get 5 is equal to b to the 5th. So we're just going to end up taking the 1/5 power of both sides, and that's going to end up giving us b to the 1st, which is just equal to b. So b is equal to 5 to the 1/5 power, and so on our calculator we get 5 raised to the power of 1/5 in parentheses, or 0.2, and that gives us 1.38. Okay. Now we're doing 33 is equal to 66 times b to the 15th, and so we're going to divide both sides by 66, and we see an equation that's actually familiar. So this would be the equation that we could get to if we had something that had a half-life of 15 time units, days, years, seconds, whatever it is. Okay, so we're going to raise both sides to the power of 1/15, the same method we did above to get b. And that's going to give us 0.5 raised to the power of 1/15. It's going to give us a number that's considerably closer to 1 than is 0.5, and we end up with 0.9548. Okay. Okay, in C now, we're first going to do the easy thing, divide both sides by 21,000 to get 2 is equal to 1.072 to the x. Okay, so what this is asking us is if we're multiplying by 1.072 each year, let's say, for x years, we'll get to 2. The question is, what is x? Well, again, this is one that we'll solve by setting up on our graphing calculators. We'll have y is equal to 1.072 to the x, which in this case, because the base is greater than 1, so it's going to look more like this. And it's going to cross here at 0, 1.072, and eventually it's going to intersect the line y is equal to 2, and so we want to find the x value of that point of intersection. So when we set up our calculator, we have y is equal to 2, and then we have y is equal to 1.072 raised to the x power. And when we find the intersection point of that, so that ends up giving us a value of x is equal to approximately 10.67. And at that point, of course, y would be equal to 2. Thinking about setting the window for this in your graphing calculator, you know that you want to be able to show the x-axis, so you want to have a y value that's below 0, y minimum. You want to have a y max that shows our line y is equal to 2. We don't need to show much beyond that, so you could set the y max at 2.5. For the x max and x min, you certainly want to show the x-axis, so you want to say maybe -1 to have the show the y-axis rather, and then you're going to have to guess a little bit to see what the window is, the x max value that would show you where the two lines intersect, or where the curve and the line intersect. Okay. All right, going to our last. So we're going to do some graphing. So we have f of x equals a times b to the x, assuming a and 1 are both greater than, I'm sorry, a and b are both greater than 1. So this is going to go upwards, and it's going to go right through the point, 0a, and just keep curving up like that. So this is y is equal to a times b to the x. When x is 0, b to the 0 is 1, so y is equal to a, which gives us our y-intercept here. Okay, y is equal to ab to the negative x. What we've done is we've replaced every x with its negative values. So this point, for example, would now be over here. And we would just end up reflecting our original function across the y-axis. So it would look something like this. It would still have the same intercept, and it would just be a reflection across the y-axis. Okay. C, negative a, 1 over b to the negative x. Okay, a lot of negatives going on here. All right, we already know that replacing x with negative x reflects everything across the y-axis. What about this 1 over b? Okay, so let's not look at the a for now. 1 over b to the x is equal to b to the negative first, because that's what 1 over b is, to the x is just equal to b to the negative x. So 1 over b to the x is just equal to b to the negative x. So that means that 1 over b to the negative x is equal to b to the negative 1 to the negative x is just equal to b to the x. So then we just have to think about, well, what does this negative a do? Well, that just now takes all our y values and replaces them with a negative, so it just ends up flipping our function over the x-axis. So what this whole thing ends up being is we're right back to the 1 over b to the negative x takes us right back to our original y equals ab to the x function, but the negative a just reflects it over the axis, and so it'll pass through the point 0, negative a, and we end up with something that looks like this, just a reflection. Okay, and then finally we have ab to the 2x, and as you recall from our previous unit, when we replace x with 2x, what we end up doing is a horizontal shift or compression, and in this case it's a compression by a factor of 2. So every x value is moved, so this point right here, to a point that is twice as close to the to the y-axis. So we end up with something that looks sort of like this. It's still curved, and let's see, let's pick some different color here, so I have those options. And then down here, it still passes through this point, but now by moving closer to the x-axis, or y-axis again, I'm sorry, we would move, instead of moving to the left, we move to the right, because all of our x values are to the left of the axis now, so they're going to move closer, so we're going to end up with something that looks like this. So this is ab to the 2x, this is ab to the negative x, and this one down here is negative a to the 1 over b to the negative x. Now we are